Good morning, everybody. Thank you so much, Daniel, for the very warm introduction. Okay, I won't test your energy levels, as we already did that at the start of the session, but just wanted to share that I'm also very, very excited to be here. Genuinely, like, I've always wanted to go to Mumbai, so coming for a drone event is actually the perfect excuse to come with the team here and meet all of you. So Daniel already gave an introduction, maybe just a little bit more about the drones team itself. So actually how it started, why are we looking into drones in the first place, and also what's the team about. So around 3 years ago, we started seeing a lot of drone parts being manufactured at our contract manufacturers around the globe. We have hundreds and hundreds of contract manufacturers in every country, and we saw more and more parts being printed, actually including India. And so we started actually asking, why do we see parts being printed for drones in our technology? So it wasn't a push from our side, it was actually trying to understand what's going on here, right? And that switched actually into a kind of organically growing team. It started with just me, and then we added more and more people as we grew, and now we are a team with technical consultants focused on drone designs. We have aerospace design engineers that bring that aerospace knowledge for unmanned aerial systems. We have business developers that know the language as well. So we have a very interesting group now that can help companies all over the globe with this. And actually, we've seen a tremendous growth in those 3 years, so it's been quite incredible. I guess someone is selling fire alarms next door, so I hope you can still hear me. Well, I'll talk a little bit louder. So I want you to have 3 takeaways today. One is additive provides tremendous value to the aerial system space. 2, multi-jet fusion, a technology we'll talk about, is the go-to solution for drone components and also entire airframes that we can build. And the first fully 3D printed aircrafts out there, unmanned aircrafts, with a 2-meter wingspan, both in defense and in commercial, are both actually done in multi-jet fusion. So I have both of those as an examples with me. Lots of parts with me, so also encourage you later to take a look at them. So one very interesting phenomenon from talking with hundreds of companies in this space over the last years is that there is very common doubts about additive manufacturing. Actually, many companies are using it one way or the other, but they use it for prototyping, right? Which is great. Actually, it's a very good idea because when you do a new product and you want to iterate really fast, 3D printing is a really good fit. But then when you look at going beyond 3D printing, actually, we hear typical doubts, like it's only suitable for prototyping. It's not a production method. You can't scale this up. It's not durable, it's not repeatable. Those are things that sometimes we hear when people are not aware of what 3D printing is about. And actually, this may be true 15 years ago, but there has so much that has changed in this space. And so today, actually, I want to show you that it's not just a good technology, it's actually a superior technology for printing entire airframes today. And I'm not comparing this with other 3D printing techniques. I'm starting to compare this with conventional techniques in the aerospace side for unmanned systems. I'm talking about carbon fiber and glass fiber and foam systems, okay? And I want you to see from today, my objective today is to show you that this is suitable beyond prototyping, that it is being used in the field, that those drones are flying, that you can produce them at scale. We'll see some examples, that you can scale them with our technology and our technology alone, and that parts can be on the drone, you can print them repeatedly, and basically your UAV can actually fly further than it would with conventional technology as well, which is a key asset that drone manufacturers are looking for, right? So it's not about just that it can be done, it's faster, it can be less expensive, it can provide you more flexibility, and so this is what we'll look into today. So I have quite a few topics to cover today. So a little bit about what applications are being done today. I want to kind of take you with me on a journey of some of our customers, go step by step in what they experienced, both in portable drones to start with, and then actually a vertical takeoff and landing aircraft. Tell you a little bit how you design for scale. I'll tell you a very interesting success story that we have in more detail, and we have lots of parts here, from a project related to wildlife conservation, so saving wild animals in Africa with drones. Doesn't get more interesting than that case, at least for me personally. then how to design your drones to actually extend your flight range, how to produce drones not just in factories, but actually anywhere in the world, and then how we can actually further optimize that production when you start scaling with what we call process development. Okay, so again, lots of topics, and even we can enter, if we have time, we can talk a little bit more about the maritime industry, and we have some time for Q&A as well. All right, so let's kick this off. So first things first, when we talk about drones, where do we see drones being used using MJF? I told you before that we see a lot of parts being printed. There's across a lot of different industries, but if I have to pick a few of them, it's those ones. So first, we saw a lot in agriculture, large, vast areas of crops, right? And you want to monitor them, when you're going to harvest them, what's the status of them. Doing that manually is a pain. So actually, drones is a very good fit for that when you have the right drones. And that's where we first started seeing some traction. Then on the healthcare side, actually first starting in Africa and then, let's say, expanding now to other places, is actually bringing medical supplies. So think about blood supplies, think about critical medicine, defibrillators, things like that, that are being used by several companies to bring medicine around, which is a really good sweet spot, right? Every second counts. The other drone you see on the right, the security one, actually is a drone printed in our technology and is flying as we speak in the port of Antwerp. So from a security standpoint, again, a harbor, port of Antwerp, one of the biggest harbors out there, it's really hard to do that manually, so having drones flying around and inspecting is actually a really good sweet spot again. Entertainment shows with drones rather than fireworks, and also FPVs. This is also, we have a few customers that do tens of thousands of drones and have MJF parts on them for fireworks, for the light shows that they do. And then two very interesting pillars. So one is last mile delivery, so the last area of delivering goods. That one is especially growing in different countries actually. In the US, as an example, there are 5 companies that got FAA approval to do last mile delivery in specific states, right, as a pilot, and then they're expanding that. 4 out of 5 are using our technology in one way or the other. Right, so that gives you an idea, and actually we'll talk about one of those companies actually disrupting even those 5, using our technology even more. And then there's defense as well. So on defense, given the geopolitical situations, there's a lot of things happening in the defense side, right? So we also have drones being produced in that area. Now, when we talk about 3D printing drone parts, what are we talking about? Actually, it's a very big range. Just to give you an idea, you can think about complete airframes. We'll talk a little bit more about that. You can talk about entire wings. I brought a few with me to show you later how that works, but there's quite a few wings being printed. Ducts of, let's say, engine-related ducts. Also a really good fit with the airflow. You can actually make it very efficient with our technology. Propellers or propeller housings, that's another one. We'll show one example where actually you can reduce the weight a lot by 3D printing it. Custom components, think about gimbals, different housings. This can all be done in 3D printing as well, another really good sweet spot. Engine covers, I'll show you this now, and then prototyping as well. It's still a good application to do parts really fast. So this is just like a small grasp. There's a lot more other parts being printed, but it gives you a first idea. So actually battery packs is one, just to point 2 out, like batteries and propellers, and then we go back to the kind of the airframe side and the customer journeys. So actually when you have battery packs for EVs or battery packs for electric drones, they use pouches, and pouches are basically very soft, flat, flexible packaging for battery power, right? So they actually need to be protected really well. If they get hit, you can actually end up not charging well your batteries anymore, right? So you really need to protect them well. And you want to protect them well in a drone while also being very lightweight, because every gram counts in the air, right? So actually doing this in 3D printing is actually a really good sweet spot. The parts were a little bit too big for me to carry from Barcelona, but we have some battery packs that you can see here in the picture. And it's really about kind of how to protect it with the minimum material that you can take, actually move away from the typical rectangular sizes, because you can actually play with the designs as well. You have design freedom in 3D printing. and actually make custom solutions. For one solution, one drone, you want to have more battery power than the other one. So you can actually play with that around as well. I mean, it's like the heart of the drone, right, in a way. So you want to keep that protected. And we've shown that this works because we have lots of drones flying with battery packs protection. Another one here that is actually propellers. So typically, when we talk now with customers about airframes, they don't realize that also even propellers can be printed. So, and they actually tested us. They said, for our applications, your propellers will simply break. So we made a demonstration with their original propellers you see on the table, and then the propellers that we printed for them, and we showed them that they don't break. You can fold them, and you can actually turn them back, right? For entertainment FPVs, for example, this is a really good sweet spot because they get hit all the time and you want to protect them as much as possible. And we see a case where people are protecting the propellers, but in some cases you can actually print the propellers too, and they won't break with our technology. And by the way, having propellers from, let's say, like the typical standard propellers, they're perfectly fine, but there's more and more cases where people trying to have local production of propellers, and that's one reason why people do it. Also, when you start printing, for example, an airframe, you actually have some free space in there. You can just pop some propellers in and print them kind of for free with your actual airframe. So there are some techniques why this makes sense. All right, let me take you on some design journeys of customers. So first, a customer from Spain called UAV Works. So they've been building fixed-wing aircraft, different ones that they have done in the east part of Spain, Valencia. And you can see here it's quite a hassle. So they become specialists in actually UAS technologies for security, for defense, for surveillance. They're actually flying in the Mediterranean, looking for illegal fishing operations and things like that. And it's a really good kind of sweet spot with our technology, as you will see. But when they started, they didn't actually know much about our technology. So they kind of used the typical conventional way of building aircraft. And that actually transitioned from what you see in the left is like 2016, to the middle, which is 2018, to the side, which is 2021, and then in 2023, they launched the Velec, which you see on the bottom. So the Velec actually has 3D printing on it, and what they basically did was, at some point in the development cycle, they said, okay, I'm going to use as much carbon fiber as possible. Everything that cannot be done rationally or technologically with carbon fiber, I'm going to use this technology that you told me, multi-jet fusion, on it. And actually what ended up with is actually a drone that has a lot of multi-jet fusion on the drone, right? You see a lot of different gray parts. All the gray parts are basically our technology. So the front side, the covers, the propellers, internal components as well, and the ailerons are also 3D printed. So it's quite a few cases where this was applied. So actually next to just replacing them with parts that actually can be done, also they were able to consolidate parts together and able to kind of produce less parts and do less assembly. Because if you start having big orders, you want to have as little assembly as possible, right? So just to give you an example, the covers that you saw on the back, so these covers were printed in our technology. Actually, they are not really printed in an optimal manner. You'll see some parts now that are much more optimized for it. Those square structures that you see, this is not really the best fit necessarily. This is actually before we met them, but we were really impressed when they started showing us the drone that they actually, all the screws that they use for those covers to close them, they actually had integrated the design into our 3D printing solution. So when they actually create the cover, they create both the screws on both sides so that you just screw the thing together. You don't need anything else to put the drone together. So it was actually a very nice way of doing this. And another example here, the propeller housings that you saw, right? So they actually were struggling with weight for the propellers because if they are too heavy, like your drone starts not having the right balance, right? You need the right center of gravity, and every gram is important here. So in this case, actually what we were seeing is that in order to get to the right weight, they had to really do some 3D printing work. And they did some 3D printing work first with FDM, and they did a lot of efforts to reduce the weight with FDM printing, different materials, and they ended up still with a propeller that was too heavy. So they had to look into, what do we do now? Can we make the specific channels that you see here on the right? Can you create channels? Can you make it hollow from the inside? How can I reduce more and more the material to make it even further? I need another 20 grams in order to make this work, because I actually have multiple propellers. So if I have 4 propellers, just 20 grams will save me 80 grams, right? And in this case, that was what they were looking for. So if you look here, actually you can see the differences. So it was at 95 grams on the left with the whole thing, actually not just the housing, but also like the electronics and the propeller itself. And on the right, it's actually 75 grams. So it's the 20 grams that they needed just by switching technologies, because our material actually has a higher strength to weight ratio, and so you can print it thinner and have the same amount of strength that you need for your application and actually reduce the weight of your entire aircraft. So it's a very particular example, but it's actually a very relevant one. I just want to cut 80 grams. Can I do it by cutting weight of my propellers? And in this case, the answer was yes. They also did we talked about customizations before. They have a very cool case on customization. So they said, actually, they got an order from the Spanish fire department to have drones that can actually release little balls that are sensors after a forest fire. We're seeing more forest fires everywhere in the world, right? Because of climate change. So what they want to do is make sure that when a fire is stopped, they can actually anticipate that the fire stays out, right? So they drop sensors all over the place in specific areas. Now, how do you drop sensors fast? In an area that just had a forest fire, drones, actually a really good application. So they actually modified some of their drones. As you can see here, their entire system here to hold these little balls is 3D printed with our technology. And then the housings of these sensors to protect the sensors when they're falling is also printed with our technology. So it's actually a whole package, basically. And then the drone would fly over an area where the fire were just stopped, and the sensors would be dropped, and actually it will open upon impact, and the sensor will be out, and it will be measuring and sending data to the fire department, right? But it all started with, how do we even effectively deploy this? What system do we need to build? It's going to take us a lot of time. Actually, with 3D printing, they could prototype it really fast, make some iterations, and then also include it for both the sensors and the whole system. So it's actually a really cool example. And then for other drones that they were doing for their quadcopters, they're starting to build as well. They have like big electronic housings. We talked about the battery packs, but there's also typically electronic housings with a lot of connectors and stuff. You see it on the right side. So actually what they did is 3D print that entire housing in one shot. Took them some time on the design side, right? But as they learned more and more about our technology, kind of from simple covers to like more advanced propeller housings, to then starting to go to these custom solutions, they're like, let's take it one more step. And they started building basically full electronic housing that are completely customized for the drone that they are doing it for. And all the connectors that you see here are integrated into it. So this is actually, I don't have the part here, but it's a very impressive part when you see it in person, and really taking the most out of our technology. And then they said, okay, so we now have done a few drones, and we started to put more and more 3D printing parts into it. Can we take it the next level? So can we build a drone that actually is fully 3D printed? And so they came up with this drone that is 96% 3D printed, and it's actually a foldable drone. It's called the Hunter. They had to make a small drone that was portable. And so they 3D print the drone basically completely. All the covers that you see here are printed. The mechanisms on the outside, the arms, are also 3D printed. Those are the ones you see on the bottom. And then basically the fuselage is completely hollow, really printed on the limit. And so together, and then in the middle there's like a carbon fiber plate, and with that actually, and the engines itself, everything else is 3D printed. So it's actually a very interesting case, because you can actually fold those arms inside. So it's super light. You put it in a backpack, you carry it with you, and then when you need to deploy it, you just take it out, you fold it open, and it flies, right? It's a really, and it's just incredible how light those examples are when you have done it properly into the technology. So here you see it as well, and actually there was a lot of consolidation of parts, so the fuselage are actually just 2 sections. The arms are directly integrated, so it's just a couple of parts, and within minutes you have the whole thing assembled, which is, you know, not typical in the drone side. And then next to that one, actually we have another case that is very interesting, next to kind of the portable one where you want to extend it with propellers and you want to, let's say, bring it and then make it bigger. You can also have smaller drones that you want to use for rapid deployment and reconnaissance. And for those, the drones actually need to be even smaller. And you really need to think about kind of the structural integrity of the parts. How can I make it as small as possible? There's actually from Nico, which is a big supplier for 3D printed parts for the US Armed Forces, and they were asked, can we make a drone that actually can be rapidly deployed, so rapid deployment and reconnaissance missions. So imagine you are somewhere and you want to have a drone with you and you want to explore an area before you go there. You need a drone that you need to carry around with you, and soldiers already carry tons of stuff with them, right? So what they're trying to do is, how can I make a drone that is as light as possible to not make their lives as comfortable as possible, and have this with them as a safety measure. And so they worked with us, they worked with Autodesk, actually to come up with this side. And also they wanted to do it because they wanted to experiment it, so they didn't want to get expensive tooling in and then realizing, that the design was going to change again and again and again. They wanted something that can be printed fast, can be deployed fast, there's no waiting for toolings, no expensive cost in toolings. How can we do this and then actually have a technology that we can use to scale that up when demand grows? So let me show you this. There we go. So this drone actually is printed in only in one shot. So here you can see it. Actually, both the area where the electronics need to go in and the battery needs to go in, together with the areas that go to the propellers with the electronics. All of this is basically printed just in one shot. There is no airframe assembly, nothing. So you just add the electronics, the battery packs, the camera, etc. to it, and you have an extremely light drone that you can use. I suggest you later come and you pick it up, because you'll see how light it is. And actually we're pushing the boundaries and making it even lighter now. But the question is, why does it look this way, right? It doesn't really look like a typical drone. Well, actually what they did was trying to see how can we optimize the heat dissipation when the drone is flying and still keep the drone, like say, strong. So it needs to have, in certain areas, needs to be very strong. How do we make the part as optimal as possible given the design freedom in 3D printing? And so they've been starting to put initially ladder structures. They've been looking at how can we optimize the cable management. So they've been looking into different, let's say, structural beams in order to make this work. And actually the structures that we have now, it starts to become very, very challenging to even injection mold it. Like you look at the optimal design, then going back to conventional production actually starts to become having features that you just can't really typically do in injection molding. There's actually several steps you see on the bottom that you need to take in order to do it in the Autodesk software. And they actually have a white paper that explains a little bit the steps that they took from a design standpoint, but it's basically different steps in terms of a topology optimization within Autodesk. When you start putting in where is going to be the areas where the heat is applied, what is the areas that need to have more strength, this is where it starts like to be able to design it. And another case of a portable drone you see here. So this is actually, this is from Unusual Machines. This is a company that manufactures and sells drones and components of drones under several, like a big portfolio. So they have Fat Shark and they have Rotor Riot as a store. So those are actually very popular under FPV enthusiasts in the US and also more increasingly in Europe. And they basically sell these small acrobatic drones that you see here directly to consumers that are very excited about kind of doing crazy things with drones. And the one that you see flying here actually has our technology on it. And they introduced a Skylight, which is a drone that you see here. Actually, the drone itself is like a standard drone. They already had it before they come to our technology, but they were looking for a different problem actually. They were looking how can we protect our drone, because given the type of missions that we are doing, it is constantly crashing, right? So we have let's say we have customers that constantly fly our drone in trees, in walls, and the floor, like this thing is gonna break, right? But how can we minimize those breakages as much as possible? Can we make a material that is flexible so that but it's still strong enough to protect our propellers as much as possible? So they came up with the design that you see on the left. So this is basically the Skylight protection of all the propellers. It's very light material. Actually, we have it here in the HP Reddington booth that you have here on stage. And it's not only very light, but it's also flexible. So it's an elastomer material. These are all very hard materials, as you can see. Those is an elastomeric, so it will bounce back. So if it crashes, actually it has this impact resistance that comes with it. So that's kind of an important feature for it. And then while they did that, they actually tried to integrate as many of those parts in one, so they don't have to be worried about assembling these little things together. It's just printing a bunch of them, putting them on their drone, and let's go. And also when they need spare parts for those, someone crashed their drone, they can easily send those parts along. All right, do we have another case? So this actually is also MJF parts that you see next to the carbon fiber of a drone from India. That is this one. So this is the Athera, actually, from a company called Vecros. And it's basically a AI-powered quadcopter, and it has some very interesting design features that they put into that drone. The drone itself is to basically use for real-time inspections, for mapping out 2D to 3D imagery, basically data collection, report generation. So that's kind of the AI-powered side of it. But it's a really interesting aspect because when they developed it, they looked really into how can I optimize I don't want to just build a quadcopter. I want to build a quadcopter with different features that can be very interesting for what we do. So we want to make sure that we take the most out of the technology as we go. So some of the lessons that they had was actually looking into 4 areas. So one is more the structural side and the aerodynamic side. So as you saw here, actually the design looks pretty sleek for a quadcopter. But the thing is that it was not just for the aesthetics, it was also to actually have a very efficient airflow on the sides of the drone, where the air passes above the propellers. So they could start including features that helps to optimize the airflow of the drone. And then also it needs to be robust, right? It needs to be a structural chassis, so it needs to be robust. Aerodynamics with robustness. That's where our technology and design freedom again comes together. Then also they wanted to include different sensor mounting protrusions, and they wanted to look at how can we include those without adding more weight. How can we add vents actually on the sides so that we can dissipate the heat, but in a way that these vents are semi-closed, so there's air coming out but no water coming in. So they made some very, very smart vents in that sense, semi-closed vents, in order to do that air transfer while protecting their internal components. And then they wanted to make sure, again, when we start getting big orders, we want to make sure we don't spend much time on assembly. How do we do that? So they looked at how can we make locking mechanisms. So actually the 4 arms of the quadcopter, you can again fold it. How can we make also those locking mechanisms to fold it and to lock it into place? How can we make them into NGF as well and actually do it in a way that it doesn't add more assembly to it? And then they did actually a lot of iterations, like how can we make the best one? We just print a bunch of them, right? We did a bunch of different designs. We don't know which one is the best. We just test them. We do simulations with them. So they actually printed several of them, and you can just go really fast. You print one, you try it, doesn't work. You print another one, you try it. So they try to really build this kind of rapid development engine, and frankly, the ones that do in the world of drones today, they are successful because they adapt super fast and they just go to the core of innovation, which is like just raw prototyping of new models. And if they already have a model on the market, they're looking either how to improve it, or typically they look for the next drones that are coming through the pipeline. How can we do innovation even faster? We have some customers that have a lot of engineers, and I'm talking engineers in the space of aerospace design, I'm talking about mechanical, I'm talking about electrical, and even those, they want to go so fast, they're even asking us actively for support on certain cases of our team in order to make that go even faster, trying to become the most, let's say, the fastest company in R&D in drones. And this phenomenon is not that common in other industries, right? Automotive is very innovative, but it takes some time to bring a new car to market. In drones, this is very different. So it's a very unique way where people can just move really, really fast. And actually, this drone, if you want to have it in different colors, if you want to have it in different finishes, you want to make it look glossy, you want to look at matte, they can easily do it because, again, you can customize between each drone that you do, you can customize what you actually deliver. All right, let's talk about a vertical takeoff and landing aircraft. This is the Blue Flight model. So this is a company in the US doing last mile delivery. That's what I was telling you, one disruptor that is trying to disrupt the guys that have all FAA approval, like the Googles and the Amazons out there. They're trying to get into that market, and they're doing really, really well. They actually were on the US television just a few days ago, showing their drone models there. So they focus on last mile delivery, meaning they need to get as much as possible out of the drone. If you want to make deliveries, you have a certain range you cover, you want to make sure that range is as big as possible, right? If people live in some outskirts and you need to deliver to them, because if you provide the service, it needs to go everywhere, you want to make sure you put the least amount of drones out there to cover an entire state, right? So performance is key, which means weight is key again, right? So they actually built a drone at the same time. They said, okay, but I'm not just about flying as far as I can. I'm also about, I want to arrive, and when I have an Uber Eats order with me, I want to make sure that it's not all over the place inside the cockpit, right? How do I make sure that it actually doesn't get stirred all over the place? Because if you have a typical drone, they would fly like this, and good luck with your dinner, right? So how do we balance these two? So they actually made 4 tilting motor arms that you see here. All 4 arms are basically tilting, so the fuselage stays stable and everything else is turning around, right? To keep the fuselage as stable as possible under different weather conditions, different wind conditions. So they took kind of last mile delivery drone design to another level, which is very interesting. And by the way, they do last mile delivery of groceries, they do it of Uber Eats and stuff like that, so food, but also industrial supplies, medical products. Think about blood that they're sending around that are urgently needed. Think about actually supplies, even in defense now, they're starting to enter where they're trying to bring things to the front line. So you have, let's say, a lot of different applications that you could use it for once you have a delivery model, let's say, right? Now they look at other 3D printing technologies, actually, when they started looking into it, and they looked at FDM, they looked at SLA, they looked at SLS, and actually all of them didn't work for what they were looking for. So they were struggling for each of them in a different reason. SLA actually doesn't have the features, let's say doesn't have the strength, so typically it's not used in this sector because the moment there's an impact, the drone falls apart. You don't want that, right? You need some protection. FDM actually has other limitations in terms of design freedom, in terms of weight, in terms of strength in all directions, because it's not actually, let's say, isotropic in properties. There's 2 directions where it works really well, and another one it's not. So you don't have the full strength in all directions, whereas powder bed technologies start to have a better mechanical property sense in that sense. Then they looked at SLS, and their plane was actually too heavy. They were 25% too heavy to be able to do what they needed to do. So they came to us then, but that was after a very painful journey on other technologies, right? And don't get me wrong, other technologies are also very good technologies. They have all their own sweet spots in terms of kind of airframe designs. Like we're the ones that have like just a very strong value proposition in that field. So one of the reasons why heavy is a problem, not just because of what I was telling you, you can't do your entire range. Actually, they're not allowed to do that neither, because in the US you have different classes of systems. For those familiar, you have group 1, 2, 3, 4, 5. And so in order to do it as a drone delivery, if you're too heavy, you fall in the next category, right? And drone deliveries, they don't want to have military type aircrafts delivering your dinner, right? They want to have, or your blood supplies, they want to make sure that's actually smaller aircraft. So they give actually a weight limit. It's not just about size and speed, it's about weight as well. So they put a certain weight limit. In this case, it's 55 pounds. And actually the regulations also say that it needs to be scalable. So if we start with 10 of them, we need to make sure that we have a path to actually have a lot more later on, right? But weight was the #1 thing first. So they look at a combination of different techniques. What do we do? And they actually needed to import what we call Class A services. They used CAD design software in order to build this. And then from there, they're looking for topology optimization. How do I make sure that I use the least amount of material again? So in order to use the minimum amount of material, what do I do here? And they use NTOP, topology optimization software, that creates then what we call a variable thickness skin. And then they started introducing lattices. So you can see, for example, on the bottom one, you see the lattice infill inside where the wing comes out. This is a side cover. And so inside actually that wing, there is all these lattices being put in order to protect the drone. Because then when you start pushing it, it actually has a lot more protection for the drone. And then they use actually isogrid ribbing. So these are like triangular ribs used in aerospace to stiffen the structure. So what you don't want to do, and what's actually a very common mistake at the beginnings, is if you want to make a cover, you make a cover just like a cover, like you would do in injection molding. That's not going to work. It's going to be very heavy, actually. What you want to do, and how you make parts lighter than injection molding or other technologies, is to make them much thinner and have a balance between the thickness of the outside, which we call the skin, and a certain structure of the ribs that actually enforce the part. So you can see here actually a kind of like a hexagonic type of structure, like biologically evolved structure, in order to provide that strength. So the little cells in the middle, they have limited strength, but they have enough strength to do what they need to do, provide aerodynamics. On the outside, from the inside, they get protected with those ribs, and then those ribs actually have a lot of strength. So even if the drone, for whatever reason, gets damaged, something hits the drone and it hits one of those cells, whether it's a big cell or a small cell, depending on the design, actually the structural integrity of the drone is there because the ribs are still there. The skin is just for the aerodynamics of the whole thing. But you want to make sure that your drone, half of the airframe weight without any electronics inside is the skin, half of the weight is the ribs. If this is unbalanced and you have a thick skin, then you start to have a really heavy drone, right? And then the last step, they implied some more design parameters in order to actually further optimize the design. So you have a lot of different steps that you need to take in order to get there, but they have been actually automating this process as well. So why do they do this? What comes out of this? So they have several very good benefits coming out of this. So one is their weight. They had to reduce the weight, but they can't compromise performance, right? So this is actually what they did. So they were able to achieve that, again, by using the strength to weight ratio, the ratios of ribs versus skin that we talked about, and then also wanted to make sure, because remember, the FAA said also make a system that is scalable, so they made it a way that actually there is a repeatability when they increase. So if I print now 100 parts, I want to make sure that all of the 100 of them look the same, right? I'm going to build 100 drones, 1,000 drones, 10,000 drones. I need to make sure they look the same. I don't want to be messing around with that. And that's actually what they did. So we worked on the production side as well to make sure that every part that they print looks the same. Then they leverage a lot of freedom for design. So the drone actually, it looks very sleek, but it doesn't look like a typical drone because It's kind of a futuristic type of design, and that's only possible with kind of using that design freedom. And then they put a lot of components in their drone. So when we actually announced, let's say, the case study with them, with parts that you see here on the left, we had 48 parts with our technology inside their drone. Today, they have already 70 parts in their drone. So they actually keep adding and adding and adding. Sometimes they ask us some questions. Can we do this? Can we do that? Have you seen this? Have you seen that? We give them some guidance. And actually already they are very autonomous. In the beginning, they were struggling a little bit, which makes sense. It's a new technology. It's a new way of building airframes. And now they're starting to get really, really autonomous and kind of constantly evolving the next designs and the next designs and the next parts. And even they did, like, next to the battery covers, the body panels, all this stuff is 3D printed with our technology. The mounts, but also even the landing gear, like the big landing gear that you saw, I think it's in the picture, if we go back. The landing gears on the bottom, the big legs, they're also 3D printed with our technology. So all these little features kind of coming into play. So what benefits did they have at the end then? So they had to reduce it by 25% versus other 3D printing technologies without losing structural integrity, without losing performance, and they did. So they were able to reduce it by 25% in terms of mass, which is massive in this space, right? And then the modeling time actually that they needed in the beginning, it took them 4 weeks to build a drone. It took a month to design the drone. And they were the different steps we were talking about. They'd spent a lot of time optimizing those steps and putting plugins into NTOP, plugins into the CAD software to actually make that faster. So now they can model those same type of structures in 4 hours. So this is what we're telling you about how do I build an R&D engine for drones and constantly coming up with new airframes just like that without carbon fiber autoclaves, without glass fiber, without foam, without injection molding tooling. Like, this is the way. This is how you can get really this engine going. All right, let's talk a little bit about designing to scale. So we talked a little bit about scaling. So one of the doubts I was showing you at the beginning is, can you actually scale with additive manufacturing? So I took a drone as a sample. It's actually in the HP Reddington booth. It's about this big. It's a drone for a company called Serveo. They are based in Spain, and they basically have those drones for all their engineers or the technicians that go out there and need to do reparations, and they need to inspect something. But sometimes they need to inspect things on buildings, on places where it's really hard to go. So what do? They figured, we'll just build our drone that is specifically for what we need. So they first started doing something similar, I just saw with Blue Flight, and with Nico, the rapid deployment drone. How can we make a drone that is like as light as possible and still being super, super strong? And so this is what they ended up with, the drone that you see here. Again, like this size. It's super light, but it's very strong. You can squeeze it all you want, it will not break. I encourage you later, pass by the booth, give it a hand, because you'll see that it's very strong. It's actually just printed in 2 components, so it's the body that has underneath actually all the structures to put the batteries in and to put the cameras in. And then on the top, there's a little cover that they put 2 screws in order to, after they put like the battery inside, they close it. And actually we told them, for your next iteration, this is really great. For your next iteration, think about some design techniques in order to remove screws. We actually have drones that don't use any screws, because then it's much easier for an assembly standpoint and for a serviceability standpoint, right? So just some snap fits and boom, you can actually don't use any screws at all. So I want to use this one as a example. Like, if we were to produce this portable drone frame, and can I do it at scale, right? Can I take this and take it into the hundreds or thousands? Is it possible, right? So what we did first is we take our build platform. So we have a certain build volume inside our big printers that Daniel was showing you before. This is the area that you can print. It's around this size, 380 by 380 centimeters by 284. How many drones can I put in there? Remember, there were the bodies, the covers, And then also they have propellers. So we said, we can also do the propellers for you if you want. So we added all these nested into, with materialized magic software, we nest them all together, and then we optimize the amount of parts we put in there. It's even less than 5% of space is being used in order to, but it's spread all over the bed in order to put 20 designs in there. And actually the result is every cover has 20 body parts, 20 body covers, and 80 propellers, right? 4 per drone. You can see some propellers here and there in the build. And with one printer, printing it 24/7, you can actually print 20,000 drones per year, okay? So that means in Barcelona, for example, in the center of excellence that we have in there, I didn't mention it, we're from Barcelona, HP has its headquarters for 3D printing, where we operate globally from there. And we have like 50 printers there for R&D purposes, application development, building drones, for research purposes and stuff, for customers, and we have 50 printers there. If we were to switch around like that tomorrow, we could print 1 million drones a year just in that facility, right? So talking about scale, if you have the right design, and we can probably optimize this further to put even more drones in there, you have a lot of drones that you could produce. And I'm saying that also because we have contract manufacturers. That's just talking about what we do in HP, in the center of excellence, but we have contract manufacturers all over the globe. We have contract manufacturers in India. We have them in Europe, in the US, etc. So, and they typically don't have one system. They have several systems. They have maybe 2 systems, 5 systems, 10 systems. Some have 50 or 60 systems. So when you want to scale this, this is actually a great way to bring that order to contract manufacturers. We have some customers that are that big that they need so much volume, they are printing at multiple places at once, right? They send some of the airframes to one place, some other designs to another place, everybody just producing, I get everything together, and I assemble it, and I send it out to my customer. So this kind of scalable network, you can produce in-house if you want, but if you want to use the network that we have of people using our HP printers and knowing our technology really well, specifically for drones, we have customers already that can help with that. And another example, because now you may say, okay, 1 million drones a year, that's impressive. It's a relatively small drone. I'm not doing those type of drones. I'm doing much bigger drones. I'm doing VTOLs. I'm doing fixed wing, right? So, okay, fair enough. So we want to show you another case where we've been working on. So the one on the left is actually a vertical takeoff and landing aircraft. It's actually this model that you see here. So it's printed in multiple sections as a fuselage, and it's actually really easy to kind of clip it together. Let me turn it around. 1, 2, 3. There you go. So now you have a fuselage that is put together because the way that we printed it, and then actually the structure is incredibly thin. So you can almost look through it in terms of the light, the structure. It's super light. Like, you should take a look later on this. And so we designed not only this drone, here. Activate this one. Check, check. Okay, perfect. Actually, it might be easier to do it on the table. So you have your fuselage here, right? And then you want to have your cover. You put your carbon fiber rods through it. You have a cover as well. You put it on top. You actually, it has mechanisms to close it on the carbon fiber rods that you put through it. And then you have wing sections that go with it. I don't have the carbon fiber rods here, but you would basically put them through, put the wings on. These are incredibly light. This is one of the lightest parts that you will find. It's like a 0.5 millimeter thin printed. Good luck trying to find something that is lighter. I encourage you, carbon fiber, glass fiber, foam, try to find it. I will be impressed. And it's not just, it's a very thin part, but it's built in a very smart way So when I actually put my hands together and try to break it, I try to break it and I can't, right? Just by putting the pressure that it would also experience when it's flying. So it's not just about making it thin, it's about, remember, getting the right strength for what I'm looking for, right? This may very well work for some different applications. It may work a little bit less for others, but in general, like finding this sweet spot for your application is going to pay off very well. And then you have the tail sections. Actually, there are two tail sections here that you put on top of the carbon rod in a very easy manner. And actually, we printed even the ailerons inside that. Okay, so no assembly needed for that. So to print that drone, actually, when you put all these pieces together, the interesting part is we didn't just think how to make it in the most optimal shape, right? Because if I do go away from carbon fiber, I go away from glass fiber, what can I do in order to actually produce the drone in a way that I can actually play around with the design, right? So I can make it more compact, I can think about the electronics, etc. So actually the drone is actually much smaller than it would be in another way. And the interesting part is when we design the parts, not just we can think about design freedom for electronics and stuff, we can also think about how can I make it in a way that when I put it in this big block I saw you before, right, a build volume, how do I put it in a way in there that is actually using as less build volume as possible, right? So I can produce as many more drones as possible. So what we were able to do is actually print 2 sets of drones for each time you print. So that means we're talking about in a 12-hour build, more or less, we put 2 drones every 12 hours. And that means with one machine, we can print around 1,300 drones a year. That's just with one printer. Remember, we have many of them at contract manufacturers. So kind of the Barcelona reference, we were talking about 65,000 drones a year, just with the ones that we have there, right? So another really good example, typically what we see is that customers asking for, they have tens of drones that they are selling today per month, and they are scared that if they go to 100 drones a month or 400 drones a month, what do I do? And I've had these cases, actually, where people call me from important companies and they say, Gino, how are you? I have a problem. We just got an order for 400 drones a month. And I'm like, wow, congratulations, right? That's amazing. They're like, yeah, it's much higher than we were anticipating, so we need to deliver in 8 weeks. We have a design, but we don't have actually, we don't have the means in manufacturing to in 8 weeks deliver all these drones, right? And they were thinking, they actually were doing small parts in FDM technology. They were calculating that even if they buy double the amount of FDM printers, they would still need 24 weeks to get all the parts done, which is half a year, right? So we're going to be 4 months late. And this was an order for the defense side. And I can tell you the defense side is not very flexible on deadlines, right? You can't tell them it's going to take me 16 weeks more. So you want to find a way to make that work. And so what we did in those cases, actually helping them in order to get to the production on time. But that's something that it's not just in the case that I just told you, but even 2 weeks ago I was in London at a big defense event. We were walking around, and one of the #1 cases was weight and flight range, and the other one was scalability. How do I make sure that I can actually scale up my production when I get those orders? Because when those come in, it's not going to be a half a year timeline to figure things out and redesign them and then put them into. So what do I do here, right? All right, so then I want to tell you about a bigger drone as well. So the 2-meter drone, a fixed-wing VTOL from a very interesting use case. So I'm going to play a video now to give you a quick, let's say a quick overview of the project.
At HD Additive Manufacturing Solutions, we believe technology should serve a bigger purpose, protecting what matters most. That's why we partnered with the Eye Above project to help safeguard Africa's wildlife and fragile ecosystems. Today, species like rhino are under constant threat from illegal poaching. By using the HP Jet Fusion 5600 Series 3D printing solution, we helped bring a unique VTOL drone to life, something the market had never seen before. HP's drones team partnered with the Eye Above to unlock the full potential of the MJF technology, resulting in an airframe with ultra-thin walls structured into cells that deliver an optimal strength-to-weight ratio. Made with PA-12, enabled by Evonik, the drone combines extreme durability with lightweight performance, tough enough to withstand Africa's most demanding weather conditions. And because the drone is printed in modules, if one part gets damaged, it can be swapped out on the ground, so the mission doesn't need to stop. But it does more than spot poachers. It can detect wildfires before they spread, track droughts, and monitor habitats under threat, giving nature a fighting chance.
To bring the communities, the rural grassroots communities, into it as well as drone pilots, drone technicians, and empower the communities and give them an alternative to poaching and actually make them part of the solution instead of being part of the problem.
This is how innovation should work, solving real problems, empowering local communities, and protecting life for generations to come.
All right, that gives you a quick overview of the project. So it's part of a non-profit organization called the Eye Above, based in South Africa. And what they saw as the problem of poaching, right? Animals being poached. Actually, in the first 3 months of this year, 2025, January to March, there were 63 rhinos killed because of getting ivory, right? And they have a really hard time to stop this. And so what is even more interesting of those 63 rhinos, it used to be that those rhinos are being hunted outside the natural parks. So there's rhinos in the protected areas and there's rhinos outside the protected natural areas. What happened was many of those rhinos were killed in the natural parks. So the poachers have become so bold that they enter those parks and start hunting there, which has not been common until this year. So the rangers actually have been looking into what can we do. And I'm from the Netherlands, so a small, very small country, especially compared to India. But like, if you are a ranger and you have a natural park that is the size of my country, it is a very big area to protect it with you alone, right? Like, it's a vast area. So even if you find out about some poacher being somewhere, like by the time you spot them, it's going to be likely too late. So you're always kind of entering too late on the crime scene, right? So that's something that has been a real problem, and they really try to focus on solving that. And the cool thing is that actually drones was the only way to make this work. And that's why we actually partnered with them and we said, look, we can work on this, because they called us and they told us, Gino, we built a design since 2019 to make this work. In fact, in the beginning, we never really wanted to use 3D printing at all. We didn't even want to build a drone. Like, we just wanted to build a drone off the shelf. We wanted to buy one off the shelf and use that, right? And we found out that no drone can do what we need. And no drone can actually, let's say, meet the requirements that we have. And then we build our own, and now no 3D printing technology and no conventional technology can do what we need. It's actually a very particular use case. So we said, okay, that sounds like a very challenging case, but let's give it a try, right? Because it has a really nice purpose behind it. Let's put the drones team on it and see if we can help them to solve this problem. So this is actually a quote from the owner, right, that you saw in the video, that they basically got this request, can we do something? This was actually before the surge in the rhino killings that I was mentioning you before. And they tried different drones. In fact, what they did is call to major OEMs that came over, brought their drones, and actually they failed in trying to work in the bushveld in South Africa. And that's because it's not an easy place to be. It's very hot, it's humid because it's close to the sea. The wind gusts are very, very strong. So it's not an easy area to build a drone. And actually there were several companies that I told you, some of these drones, they broke in operations. Okay, so there were several that were actually foam-based, and the foam drones broke during operations. So some of them actually came back with broken drones only. And there was one company that had something similar in terms of a failed operations trying this out in the bushveld with the eye above. And what happened was that they left some of the drones for the second day to try again. Hopefully there's less wind. And the drones got eaten by wild ants, because the wild ants there, and turned out that they eat foam, which frankly we didn't know. But so you'll see that there was a lot of challenge and frustration. They're trying to do a noble cause, but you just can't find a way to make it work, right? So when we talk about these unique design requirements, we ask them, okay, tell us more specifically what you need. So they were talking about long flight durations. They want to be out there for hours in order to work, right? Again, big area, so I need to fly a lot. I need to fly far, so I need to have a long flight duration that I can do with my model. It needs to be durable, and not just typically. We told you about the high winds. There's a lot of dust too, and there's rain. So how do we fly under all those conditions and make sure that the drone actually can do that? There's another interesting phenomenon here, is that they need to easily transport it along, because it needs to fit in a utility vehicle from the ranger. The ranger is in his Jeep. He has a truck. He has a carriage behind with the drone inside there, driving around, right, ready for deployment. What could happen is when he puts the drone out there to start flying it, there's cases where wild animals spot them and start running towards them. So if you have suddenly a rhino running towards you, you want to get the hell out of there, right? So you take the drone, you throw it in the truck, and you get out of there. If you do it with conventional airframes, they will break, and you won't be able to repair them, because if an airframe gets damaged, the typical glass fiber and carbon fiber or foam airframe that you see out there, when they get damaged, they get just tossed away, and you use a new one. But that is not going to be a good solution for these guys, right? They're going to have drones that damage just because of the nature of what they do. So they were looking into, how can I make something that's not only easy to carry around, is light, but is also able to be easily repaired in the field somewhere, right? So I need to be able to take my drone in pieces. And then they said, okay, actually what I need to do is I need to deploy it with specific cameras. I need to spot, for example, I need to use it for operations to detect crane birds. Actually, the International Crane Foundation is part of the project. Endangered Wildlife Trust is too. And one of them wants to monitor first, how many animals do we even have? Because we don't know, because there's so many. We count them by hand, but that's pretty tiring already. Can we have a drone flying and actually with AI count the number of animals that is out there, right? And then I know how many to protect. But sometimes you can actually need to change just from counting to actually look for poachers actively, which may need a different camera to look for that. And more importantly, what's happening a lot as well is that there's a lot of people putting wires of metal across the different parks and outside the parks in order to capture those animals, like metal wires. Today, they are looking for those wires by hand. There's rangers looking through the woods, looking for metal wires that would capture animals. And those wires actually don't even kill the animals that they want, because it's an indiscriminate trap, right? If there's antelopes coming, they get killed. Lions are getting killed. They're not looking for those animals. So it's like a pretty tragic story, and it's really hard to find that metal. So what they've been doing is actually, with the drone, one of the requirements was, I want to be able to suddenly change the fuselage and put a synthetic aperture radar on it that can look for metal on the ground. We're like, wow, okay, that's a very specific requirement. But yeah, it can be done. And again, 3D printing is a good spot for that, right? But having that freedom to suddenly switch from counting animals to protecting animals to looking for traps, and actually tell the ranger, hey, I found traps here, 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 and here. Go there. Go there and look for metal on the ground. Basically becoming like, the drone is becoming like a really, really good technology tool for the ranger to be able to protect this area, right? All right, so with these requirements, we move to, let's say, with the solution. So they were looking first into composite materials. We talked about this. The difficulty to repair it, right? It's difficult to repair those frames, and then you need to toss the whole thing away. That's not going to work for this case. So next to that, actually, you need to require molds. You need to require autoclaves. So that's going to also be very expensive to do it. And you're going to be stuck in your design. And honestly, they have been iterating every few months. They learn something new, and they iterate again. Then looking at foam, we talked about this, the wild ants eating the foam, and when it's not being eaten, actually it doesn't provide the strength that it needs for the wind. So you need a really thick part of foam, which then make the aircraft really to have the right strength to weight ratio, which makes the drone really heavy again and really big as well, impractical to bring along, and it's not really durable. So it's not going to survive the dust and the rain and the wind and everything together for a number of years, right? So they needed something for very advanced structures, but they can't use subtractive manufacturing for this case. So what do they do? So I told you before that they were looking at SLA, DLP, FDM, SLS, and even early MJF. It's a little bit like the story of Blue Flight I told you before. It's a little bit of a painful customer journey because our technology is not always as known as others because we were relatively later in the market, just in 2016, whereas others are there since the 80s, right? And so we've had more cases like that where a customer tries SLA, FDM, SLS, see that all of them don't work for different reasons, and then end up going with us. In this case, actually, they also told us our first printer, the 4200, wasn't good enough neither, didn't work neither. So we said, okay, let's work with the 5600 platform, the latest platform that we have, in order to do this. And with that one, we were able to make it work, and I'll tell you now in a second why. But it's not just that it enabled them, actually they were very fast in developing. Remember this engine I told you about? They went from one design to another one in no time. And I'll show you a sample of the fuselage now. And then also there is no tooling, right? So given there's no tooling, they don't need a big volumes of natural parts ordering in order to justify the business. They can just start with 1, with 5, with 10, 15. They already have orders in, but this gives them the flexibility for that, right? And they found that PA12, so the polyamide 12 material with our technology, is strong, but it's flexible and it's needed for those, it's ideal for those demanding conditions that we were talking about before. So what did they come up with? They came up with a drone that is ultra thin for what it needs. It's a 2 by 2 meter drone, actually 2.1 now in terms of wingspan, yet it's 0.8 millimeters thick. And it has walls structured into cells, that what I was telling you before, to have a really good strength to weight ratio. Test, test, test. All right, thank you, perfect. It's just a bit easier standing here. So when I talk about the cells, actually, I don't know if you can see it, but there's like very big hexagonal structures inside. On the outside, it's flat, right? On the inside, hexagonal structures for the strength. And so you have a skin of 0.8 millimeters, so less than a millimeter, which has like around half the weight. And then you have the ribs that provide the strength. So the cells provide the structural integrity. The skin is just for aerodynamic purposes and to keep the drone together. If, for example, the drone gets hit, something hits the drone, and one of those cells gets damaged, I would pierce through it now, for example. It would slightly affect the aerodynamics, right? Because the wind will not flow through it, but it will keep flying because it wouldn't damage it that much. And from a structural standpoint, it'll be fine because the strength coming from those ribs. And those ribs, you can't damage them. They are really strong as well. Okay. Now, what's also really interesting is that they actually combined a lot of little features inside there. So they looked into how can I connect all my electronics really easily in there? How can I put structures? My carbon fiber rod goes through the middle. How do I make sure that I put that in a way that the powder is easy to remove, but I can put the whole like carbon fiber rod easily in there and it just fits right away. So they really thought through about this drone. And we're still like every now and then, we were talking about it yesterday, we steal little features that actually have certain functions that are very interesting. So this is a drone that is that it came out with. So it's a rear transition VTOL. What that means is that the rear motors at the end, they actually move like this in order to move the drone around. So it's not flying like this, it's actually doing the mode on the back, which gives them a lot more agility versus other VTOL designs that you typically see out there. It's 90% 3D printed, so all the parts that you see here, basically the wings, the propellers, housings, the fuselage, the tail section, the motor mounts as well, where they put the motors in, they're all basically 3D printed. The holders for the cameras, the radar system that I was telling you before, all of those are integrated. And so on one hand, they were calculating that they saved around $60,000 to $80,000 on tooling for all the steps that they've been going through, and almost $500,000 in R&D, in product development and prototyping, just because of the kind of jumping on our technology and us helping out them to kind of accelerate that learnings that they have, right? So, and actually, I told you before, being in a natural park the size of the Netherlands, looking around, it would take them a week to have a certain area covered. The drone does this in 15 minutes now. So if you have a flight time of 2 hours, you can do 8 times that region that you cover in a week. You can cover that now in one mission. So imagine a drone actually going from 2 months of working on foot as a ranger, now in one mission, in a few hours, covers all of that. And just signals back to the ranger, go into your Jeep and go here, 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 and here. There's where we see something suspicious, right? So that's just another level of how technology can actually help, not just drones, AI, to do that for its purpose that is actually, saving animals. Very, very genuine purpose. So they're actually deploying the first drones. We've been going through lots of testing with the authorities. We actually made, I'll tell you a little bit more about it now, about how we changed the designs in order to add some more capabilities before we send it to Zambia. But there it will be flying to protect the crane populations. And then it will go to the Kruger Park. You may have heard of this. It's like the very famous park in South Africa where there's the top 5 animals, like the lions and the rhinos, and we'll be talking about before. And there it will go into the snaring and poaching crisis. So a really exciting next steps coming. And actually, what we're doing is the local communities are going to be part of the drone, becoming drone pilots. We want to use them as like maintenance engineers, so kind of involving the community as well, as the owner was explaining in the video. All right, then talk a little bit about how to design drones to extend your range. So I think by now you're starting to get the point that we have 3 pillars of our value proposition that we provide to drone manufacturers. The lightest possible airframe structures out there at scale can only be done with us. That's a bold claim, I know, but I wouldn't make it if it weren't true. So we can produce frames that are significantly lower weight versus carbon fiber, versus glass fiber, versus injection molding, and even versus foam at times. Or we can beat let's say, the weight of the drones and actually make them more efficient. So that's really kind of our aim there. Some people using it for components, and more people are starting to be interested to actually use it for airframes. And I was in May in Exponential, the biggest drone show in the world, and we had people from the US Defense coming over, looking at our drone, at the wildlife drone that we were showing there, the Bush Ranger, and they said, all our defense contractors have told us that this cannot be done. You cannot 3D print an entire airframe of a 2-meter wingspan. Everybody told us that this cannot be done. And now you're showing this, so something's off, right? And so there's this lack of awareness because it's so new, but it's already being deployed rapidly. And then it's coming from this technology of using our, let's say, our printing, a way of printing where we use agents. We have powder basically, and we use agents, what we call it, which is kind of bonding the parts together. Every time you put a layer of powder, we apply agents. HP is very good in printing, right? Printing on paper. In this case, what we do is we do the same thing, but on powder, and we calculate exactly where we want to put little particles in order to then apply heat to fuse the parts together. And so what we are doing in this way is making very, very, very thin walls that then can get fused together. Okay? You want to have aircraft that are strong, but strong enough for what you're looking for. So you have to need the right rigidity, right? Then we talked about scalability. We have the highest productivity in additive out there for this type of applications. We talked about some examples where you can go into the tens of thousands per year just with one of our printers. And then where it really gets interesting is when you start actually optimizing that process. So I don't want to produce, let's say, anything, right? We've built a printer at the beginning that can produce anything. We can produce for drones, for OMP, for automotive, for consumer goods, for eyewear, for fashion, like whatever design freedom, right? You put it in there and you print it. But actually what you want, if you're a drone manufacturer, you don't want to print jewelry. You don't want to print eyewear, right? Who cares? You're looking for your business, and that is printing airframes, printing components. So I just want to care about this. So that's where it gets really interesting, because you can start actually playing with the parameters of our print modes in order to increase the layers of the powder, for example, if that application allows you, right? In order to control the heat in a way that you can produce walls that are like 0.5 millimeter thick. So there's a lot of little things you can tweak with that won't work for eyewear because they really care about how shiny your glasses are, or for fashion, for example, or for OMP, orthotics and prosthetics, but it will really work for drones. So that's where kind of the sweet spot lies. And then actually we have the cases where people suddenly need to scale really fast. We have a lot of tools to do that. A lot of bigger systems for powder management and stuff like that. So if someone suddenly needs to scale a lot, we've been working on that since the start, building those tools in order to have a quick ramp up in production. And then what I told you before, like adapt to changing designs, right? Anyone that is starting a drone company now and is not using additive manufacturing effectively is going to struggle, because there are going to be companies that are going to do this very effectively and very fast, and there's frankly no way to compete with that level and speed of R&D with like subtractive or even other 3D printing technologies out there. So this is one of the takeaways I would take from talking to 200-300 companies now. I think this is one of the main areas why 3D printing in drones is so popular, and where people are really trying to take the most out of it. And then what's also really cool is that once you have a prototype in, you can just use the same thing for production, right? So you don't need tooling for the final products. You just use the same printer, the same material, same everything. You just bring it to production, just like that. So we talked about the eye above, right? Here you see it hanging in exponential. And then we have another interesting case. We'll talk a bit more about that later, which is Firestorm, which they use it for, let's say, Class 2 UAV, so they use it for the defense space as well. So that's another case that was built in order to scale up fast. Now, extending the range. Remember the VTOL that I was telling you before about? So here, comparison. If you would do this into carbon fiber, the airframe weighs around 1.95 kilos, okay, for the 1.5 meter I was telling you about. It has a range of 60 kilometers and a battery capacity that in total is around 2.2 kilos on battery capacity, right? So taking this, we were looking at how can we build this in a way that actually is going to be much more efficiently in additive manufacturing. So we actually redesigned the whole thing in order to make it lightweight, optimize it, and actually think about the structures. And even we could slightly reduce the wingspan in order to still get let's say, the same range, or we keep the same wingspan and we extend the range. So what you can see on the bottom, actually, where we're looking into like different designs, different weight ratios, where should we be playing, where actually is the pressure applied on different wing sections. And so in order to kind of redesign it, we took some aerospace design knowledge into account, right? I'm not an aerospace design engineer, but we have some in our team that really know all about this stuff. So we look at maximum takeoff weight, we look at wing deflections, we put load factors that are applied to the drone, and we take all of this together in order to then decide, okay, what can we do? If we start from scratch, what can we build to have an airframe that is actually thought for multi-jet fusion instead of taking a conventional drone and try to, how can I slightly change this a little bit in order to make it work in 3D printing? No, you need to think about it holistically. So actually the design that we started with doesn't actually look that much like the design we ended up with, but it has exactly the same characteristics to do what it needs to do. In fact, what happened is that the frame weight is much lighter than carbon fiber because of the way that we could build it. And then what we do is we actually kept the same weight, but by adding more battery capacity. So we said now you can actually add 800 grams more battery capacity. So now you end up with a drone that cannot do 60 kilometers in the red circle that you see in the right top. I can do 80 kilometers. And this is huge. This is a very big increase in terms of range, right? Talking about 33%. So if you go back in the case of Blue Flight, or you go back to the case of the eye above, and you need a drone to cover a certain area, now I suddenly have a drone that can cover a lot bigger area, so I need a lot less drones to do the same thing. Or I have more drones that can work in the same area now. So this range extension through 3D printing, I hope it shows you that it's not just about playing around with technology, it's not about just printing for the sake of printing, it's actually printing for the sake of getting a lighter structure that then makes your drone fly further, right? There's a few pillars that we apply for this. So number one is aerospace architectural know-how. This is what we wanted to have in-house immediately. So that is something that comes into mind. Then we use that for structural optimization. So what are the rules, the simulations, and the nestings that we need to apply, knowing our technology too. So having aerospace knowledge and have MJF knowledge and kind of fuse them together in a way, right? We got some CAD designers that are very skilled in order to then take the aerospace outputs that take the boundaries, like this you can do and this you can do, in order to make the most creative designs in that. And then we use the best printing technology that is out there for those small features. Have a process that is actually as much on the limit as possible in order to then help customers with their airframes, okay? This is a high level, like the different pillars that we touch. So there's a few things that we help with in the drones team that I think you have seen now. So a few of them is the optimization of airframe structures, right? Making them in a way that they are the lightest possible, like the Nico drone, so it can be FPVs, but it can be VTOLs, it can be fixed-wing aircraft. We can optimize the wings as well. So that's another case where we constantly look for how can we reduce the weight of those parts. The skin engineering side, so we talked about this honeycomb structures and these biologically inspired structures to actually create the ribs in the inside. That's something we have a lot of experience with now. How much stiffness do you want? Depending on that, we'll have you a new pattern. And then assemblability, that's actually a really good one as well. It's like the drone that I was showing you before, the VTOL drone with the different components. Putting them together is minutes. It costs nothing. Okay, so it's a really, really fast process to put it together. And that's where if you have suddenly scale from 1 to 100 and you just have a few minutes of assembly, you'll be fine. If you have 6 hours to build it or 2 days to build it, especially for larger aircraft, this becomes a really big problem, right? So those are areas that we typically help with. We can make morphing wings. We can include the ailerons inside it as one of the parts that I showed you before. We look at the thickness, at the chord length, at the wing length. We do simulations, how much force is being applied from a 4G standpoint. And then we use that in order to calculate what is the total weight of the MJF parts with the carbon fiber rods, and how much can we actually reduce it if we were to go for our technology. And that's not just with those. Actually, we're already doing for wings that are much bigger. We're doing it already for wings that are up to 5 meters, so a 5-meter wingspan. So that's very big drones now. So in the beginning, people were telling us, you can't do half-a-meter drones. We did it. Then at 1 meter, we did it. Then 2 meters, we did it. 2.5 meters, we're doing that. So now we're pushing to 3, 4, and 5. So we're really trying to push the boundaries of what's possible. And just every time someone says we cannot do it, actually our team is quite stubborn in that way, and it's like we want to prove you wrong and we want to start doing it right now. All right, then another a very, very cool use case used in the defense space is actually a company called Firestorm. And this all started because in the defense industry, there's a lot of changes happening, right? Actually, the industry has been basically manufacturing the same way for years, right? Since World War I, actually, they've been using it in a very centralized manufacturing way, even before that already. And so you have this kind of central startup. Even in World War II, all the machines were kind of retooled. They started producing tanks, armored vehicles, and so forth. And like, that's the model that the industry has been built for. And it's been built for peacetime. So like having central factories and just use them for manufacturing, right? Now there's a big flaw in that, and that's what we saw in Ukraine as well when the conflict started. The first week, all their factories were taken out, or all, let's say quite a few of them were taken out because it's such vulnerable. There's a big factory that produces X amount of military systems, and you just use it as, it has a big target on its back, right? And so this has become something efficient. It makes sense from a cost standpoint. We put as much demand together. We have a nice manufacturing line. We have people coming in. But once, let's say, peace times are over or are in danger, or if you want to prepare yourself in case something could happen, having factories that are centrally put are very, very vulnerable, right? And it's not just the factories itself, it's also the people that need to come to the factories, and then the goods that need to leave the factories. So there's a lot of kind of vulnerability there. So what is actually happening is that people moving toward hybrid strategies. So they're not just closing their factories, that will be another extreme, but you could actually use the same factory or smaller factories in order to still deploy a lot of parts centrally, but have a lot more hubs around it that actually distributing points or manufacturing hubs that actually can also take some of the production. This is what we're seeing in some of the conflicts today. They are printing everywhere. There's no big factories in Ukraine typically anymore. It's much more distributed everywhere, right? So having this in mind, when companies or when countries now are thinking about how to protect their countries, how to protect their borders, having new strategies in mind is going to be vital for it. It's not just about which drones I use, how many drones I'm going to have, how many can I produce, but actually what can I do from a manufacturing standpoint. And I'm going to play you a video from Firestorm that will show you a little bit of what they do.
The need for drone production is more pressing now than ever. We're talking orders of magnitude greater. We need to shore the defense industrial base through rapid part manufacturing at the point of need. We need to totally rethink how we build and how we deploy systems, and we're handling the manufacturing part of this. Part of the value of Excel is the ability to put the entire manufacturing infrastructure into a container, to move it around the point of need, set it up in less than a day, and begin production of these critical assets.
So that's a very good overview from the company Firestorm in the US. And what they basically do is, next to building drones, they actually build container cells that can be deployed in order to manufacture drones, manufacture spare parts, manufacture orthotics into the field. And so it's basically actually Firestorm is a company, it's a US company backed by companies like Lockheed Martin. They have been awarded contracts up to 100 million. And this is all public information, so they have won big contracts, and they've been basically moving ahead towards solving the problem I was telling you before of enabling people to be able to produce not just in central factories, but basically anywhere. And so you can see that they have an HP system in there. These are the industrial systems. They are going inside the containers, and they actually deploy those containers in different places. This can be at military bases. This can be in the field. This can be at very different circumstances where this is being used. So it's a very, very interesting use case because they're really trying to kind of push the limits there of what is possible. And also they do a very wide range of models. So it's not just talking about one specific drone model and just use that. You may want to have different drones, right? So you want a different drone model. So this is something that they really thought through, and their drone portfolio is growing really, really fast. So just to show you how it's actually being deployed, once it's being deployed somewhere, and showing the HP printers as well. You saw a little bit in the first video already. I have a second video that actually shows you a little bit how it works in operation. They was at a military base in the US. They arrived there and they need to deploy their factory. So this is a little bit how it looks. Don't get scared of the helicopter sound that starts at the beginning. I hope that gives you a good impression of the XL container in action. Actually, you see it here as well. Some pictures of the machine running, video of the machine running here as well. It's producing drone parts in a field at different places. And it's such a new concept that people are constantly wanting to see demonstrations of it. So the team is always out there. But what's important is what type of drone they do with it, right? So this is actually called the Tempest. And it's in the different groups we talk about. It's a group 2, a class 2 drone. And the very interesting part is not just about the drone itself. The drone itself is like a 2 by 2 meter drone. It actually can be built like out of the blue. So 2 weeks ago we were in London at a defense event. And what we did was actually build the drone on the place. So what we did was just we actually ended up with a suitcase on stage, took the suitcase out, and in 3 minutes we built the whole drone. And people were asking us from the military, what are you doing? Like, well, we're building an airframe. Like, you can't build an airframe. What's that all about? And like, well, we can. So we were basically putting it together in a few minutes, and people were just staring at us like, never seen that before. Like, an airframe is just a fully done concept and that's it. Can't just build one on the stage, right? But then we showed them something even more interesting, is that when you take from the drone, for example here, when you take the back side of it, it has a jet-based, a fan-based jet engine, right? You can see that little bit sticking out. It's actually built to fly for over 1,000 kilometers in this setup. But the cool part is that you can actually modularize it. So the software is already thought through that it can run different setups, different configurations. So what you can do is just take the drone out, like let's say the tail section with the engine. You just leave the engine inside the tail section. You take the tail section out, and you put a propeller-based engine on top of it. And suddenly you have a big propeller that you may have seen in some of the videos, and it works as well. And you have suddenly a different mission, right? You want to have a completely different mission. You don't want to send a jet-based engine to what it wants to do. So good, I'll just take this off. I put another one on. This is not a concept that exists in aerospace. You can't take a plane and just switch engines, right? But this is now something that they have been really pushing for, and that modularity concept is already, let's say, getting a lot of attention from the let's say the traditional market. Ah, yes, we can do that. Yes, we can build the wing. Yes, let's do that. Test. Okay, thank you. So I have my dear colleague and assistant helping. Yes. Okay, so one wing to show you of the Tempest. Perfect, yes. This is the full wing, basically, that gets stuck on top of the drone. And then what we do, we have carbon fiber rod that gives the rigidity that we need for the flying operations, right? And we will enter them inside it, and then we put the drone together. Perfect. Thank you, Daniel. So that was, what, a few seconds? And it was Daniel's first time, actually, putting the wing together. So that gives you an idea of how fast you can put a whole drone together, right? What's also interesting is that imagine you are in the middle of nowhere. You are in a container and you're printing drone parts and you want to put a drone together. What do? You want to make sure you have as little screws and rods and stuff like that, right? I need to easily open it in operations and I need to easily assemble it together. So one of the features is, how do I do that? And also by people that may not have a lot of experience, because I'm going to put this container everywhere in the world, right? So, for example, to open the doors, what they did was build a system that you saw in the videos that actually opened just like this. But the whole system of this is actually 3D printed. So they printed it just like that, with the whole structure and also the lock, and also actually instructions on the lock when it's locked and when it's not. For if people haven't seen it, like Daniel for the first time putting something together, he actually knows how to do it. If you would have to switch these wing sections around, it wouldn't have fitted because it has a Pokayoke approach where it actually stops you from putting the wing wrongly together, right? We don't want accidents in that sense. And then there's another interesting feature is when we have a fuselage sections. I couldn't bring the whole thing in my bag, but you can imagine you have a fuselage section here. You have another one that you want to make it, for example, you want to make it bigger. So what you can do is actually put the parts together. There's actually arrows. There's arrows on top of it that you put where they are pointing to each other, and then you just basically turn it around. There you go. And now it's locked, and actually you won't get it loose, right? Simple as that. And if you want to get it loose again, you just press there and you turn it back and you get it out again. So in a matter of minutes, you can build a 2x2 meter drone that is a class 2 drone. Again, something not seen before. And just to show you that it's not just a concept here on the table, it's actually flying. We have an imagery. So I told you a little bit about this hybrid manufacturing side. It's something still new. There's several drone strategies still being published. Every country is doing that. And there's some of them starting to think about actually how do I take the manufacturing into account when I do drone production. Think about huge factories that are producing a lot of parts, production hubs, smaller ones that are still doing class 1, class 2 drones, and then just places with one printer that are actually doing the final smaller drones as well, handheld drones that you can easily bring with you. All right, I'm gonna skip this video for the sake of time. All right, just to show you a little bit more on the technical side. So if I want to optimize their production, I talked about these knobs. What on earth am I talking about? Just to give you an idea. Actually, so the process development lets basically manufacturers use different knobs in order to make the application work. So we actually do what we call a multi-level functionality, which means that in every section of the bed, we can actually play with different features. So we can print one section thicker, one section thinner, we can apply more agents. So there's a lot of different things we can do. We can tune dimensionals as well, so we can make dimensional tunes for whatever, let's say, the tolerances that the company needs. We can play with those. So there's a lot of different recipes and parameters that we can use in order to consistently produce the same, let's say, airframe all the time. But now I'm talking about one printer. If I now go to another printer or another printer in a container somewhere in the middle of nowhere, how do I make sure that it actually produces the parts that I want to? So that's why we have job adjustments that are specifically for each build I do. I make sure that every time I do this build, it's optimum for my application. But I also do device adjustments. Device adjustments allows me to actually make sure that the thermals of my printer, the dimensional profile of my printer is actually the same. So we typically print certain builds with little stars in them in order to calibrate the printers to make sure that it operates in the window that it needs to be printed. All right, I won't go into much detail, but you can see the idea of having like reduced cycle times, higher throughput when I introduce my layer thickness. If I want to have actually very detailed drones, I make it into smaller sections. Okay? There's different, let's say, trade-offs for each. Actually, the drone that I was showing you before from the eye above, this is the design that it had in the beginning. And in the beginning, I mean May, when we showed it in the Exponential. And now it already changed a lot. So there's a lot of different features that you can see from the one that is over here. They don't look the same anymore. They actually made a lot of changes. Why did they make changes in the first place? Not just for the sake of it. Actually, because in the US it got so much attention, we realized there were rangers in the US wanting to buy this drone. So we said, okay, but there is NDAA compliance in the US. There is more strict compliance in other parts of the world too. So let's make sure that we make the drone compliant for all those things that we weren't anticipating, so that then once we deploy it and we do the 100 hours of testing and deployment, we can actually use it with a model that can be sold in many other countries not just the South African bushveld, right? There's other places that also need, let's say, wildlife preservation or drought control and things like that. So while we made these changes, actually we try to also, let's say, make it easier, because the first time we built it, it took several hours to put it together. And so we said, okay, can we do it in a way that we can actually produce the same drone, but much faster? So we said, yes, let's look at snap fits. Let's look at different techniques to do that. Then we talked about the thin walls and the honeycomb reinforcement. Can we play a little bit more with that? Yes, we can. Then we looked at internal structures. Okay, it's great to have a beautiful internal structure that you see here, but it starts to get a little bit hard to take all the powder out that is not fused as part of the part. So okay, let's play with that as well. And actually you see the structures, kind of a ladder structure in the middle of the part here on the table that shows you like where we put more area in order to get the powder out. And then we wanted to actually increase the number of parts per build, right? So can we add more parts in the same build to have less builds and make more airframes with the same productivity? Actually, we needed to change the motors, the electronics, everything we needed to change from supply chains to different supply chains from other countries. So that's where the motor mounts then need to be different, the weight balance need to be different. Actually, this one is slightly larger than the previous one to account for that. So there's a lot of little features that come into play. And then remember, a drone can get damaged, right? If it gets damaged, what do? We need to easily replace that. We don't want screws, a ranger in the field using screws. So what do? So we did several techniques. Here's one where we placed fuselage clamps. So you see here, for example, when you have wing sections, you can actually put them together like this, and you have a technique in order to then, I won't close it because I won't be able to open it anymore, because it's made not to open without a screwdriver, but you see the point, right? You just press here and it closes. And the same for the fuselage, so it has actually big sections that go on top and the bottom of it to have the whole aircraft. And so you can see the same principle applied here, where basically, let's say this is one section, I place it here, and then I press hard here, I press hard here, and now actually you won't be able to open it anymore. It will be just like this in the field. You need to tune a lot the printing side in order to make this work, but we mastered that skill a little bit in order to do exactly this. And the same actually between the fuselage. There's like a few snap fits here as well on the different sides that kind of all click. You see it here as well. They click together and then it all fits together like a cantilever snap fit joint, it's called. And it all fits together, and you won't be able to take it off. You need to go in the inside, open this, and it gets off. So you don't need screws again, but it will allow you to easily put it together. All right, several hatches that we did in the same way, basically using the same technologies. I talked about the cleanliness, right? So all the lattice structures inside. And then the thin walls and the reinforcement structures that is basically throughout the entire drone. And one actually really cool aspect that I haven't mentioned yet is this. This is actually, it says draft because we just filmed this and we haven't even published it yet, but I wanted to show it to you here. So the walls are actually so thin. Are actually so thin that you can see it's actually translucent, so the light just goes through it, so that gives you an idea how thin the structure is. Pretty cool feature. Has no function, but just to show you that how thin basically the aircraft is. All right. Just to kind of finish off, very quickly, two more things. So on the technical side, like I typically get questions about, I need to know more about mechanical properties, I need to know about water absorption, a lot of different things that come into play. We have experience in all of those areas, okay? So we have tested water absorption in the most salty waters on Earth. Turns out actually that's in the Mediterranean is one of the areas. So we've been testing water absorption to show you that drones actually don't absorb water, and so you can use it into, let's say, different circumstances. We have techniques to join parts together, as you saw, to make sure that it's fluid tight, to make sure you get the mechanical properties that you need. Some cases they need chemical resistance for some crazy missions. You can think, like there's ways to actually think about that. Light fastness, drones that fly 5 years in Africa, 5 years in the light. I get a lot of questions about that. We have actually materials that are very suitable for that. And even if you want to use materials that, let's say, are not built for that, are still good for that, but not built for that, and you want to maximize it, there's actually finishing techniques over the parts to protect them. Coating is one way, like Firestorm did, but there's other techniques also out there that protect your part without putting much weight to it as well. And actually, we have labs for dimensional accuracy, mechanical property testing, so come with the crazy ideas, we will be able to help you. All right, and then the last part I wanted to mention is that next to, we talked a lot about aerial structures, aerial vehicles. We see a lot of demand also on the underwater side, the UUV side. So there's several cases there where also our technology is being a really good fit. Think about inspections of cables deep in the ocean. We have drones that are 2,000, 3,000, 4,000 meters deep for months with parts externally in order to do those missions, and with great success. Okay, so next to the whole aerial side, there's also a lot happening on the underwater side, from defense to inspection to oceanography, studying basically the bottoms of the ocean. You need to have a drone that is able to do that in very deep waters, right? One example is the Buddy from a company in Germany. They actually developed one that is being used for basically research and development on the bottom of the ocean. Very, very cool case. And they saw that with our material, actually they got the strength that they need, and they were able to use it underwater too for the right balance between strength. Lightweighting is not so important. Actually, there's another effect that they need to balance through if you go underwater. I won't go into depth in that, but it got a really nice combination there. So it's all about isotropic part strength, very good water tightness, we talked about this just right now, and having the design freedom. Can I build the smallest drone possible, the most compact drone possible, that can do exactly what it needs me to do? So with that, I'd like to thank you for the last 2 hours of your attention. Thank you so much for sitting this through. There's a lot of topics that we covered, a lot of information that we covered. Just wanted to kind of enforce that we're the trusted solution for drones in India. I'm going to let my colleague Daniel, okay, I'm going to get some closing words here, but if you want to contact us, please know that we have, as Daniel mentioned, the contract manufacturers across India. You can reach us, drones@hp.com, the email will come to me, or you send it directly to my name card. I'll come after the session, come to us. Happy to answer any questions you may have. Happy to look into any challenge you have. The idea cannot be crazy enough for us to address it, so feel free to reach out to us after the show. So with that,